Okay, so maybe we can just start to discuss the solution. So tutorial 2, distributed query processing. I always open the chat here, the chat bot, so the chat box. So if you have any question or if you have something to say, you can put it on chat. Okay, so the question 1, distributed query processing. At the global level, distributed query processing consists of 3 main steps. And this is the common or general knowledge. The first one is query decomposition. The second one is data localization. The third one is global optimization. Discuss these 3 steps following on the input-output objective for each step. Okay, and if you study about this query processing in whatever subject, or maybe you can, or maybe you try Googling, or you try find anything about the query processing, you will find this this figure: query decomposition, data localization, and global optimization. And now before we go to each step, before we go to query decomposition, data localization, and global optimization, we need to understand the general idea of the query itself. So this is from high level query. Query is consists of the relational calculus, and this is the common statement that we use in the SQL query. Maybe I need to just stop the video to make it better, maybe. Okay, so this is the common SQL statement: select something from table where condition. And I believe you are familiar with this statement because in the practical we also use this statement. And the things that you need to pay attention in this one is here. So here you need to understand about the selection. Selection is where clause. So selection is where clause here. So selection is, let's say F is the formula, like a salary greater than 10,000 or salary less than 30,000, something like that. And then the second one is projection. Projection is the select statement, is the select command. So this is the projection. Let's say we want to project, or let's say we want to select A and B, and A and B are 2 attributes of relation R. So let's say in the table employee, we want to select the employee number and employee name. So select employee number and employee name from employee table. And the third one, this is also important one, union. So if you remember the task in your practical one might be task 1, the number 3. You need you have 3 table, the athlete 1, athlete 2, and athlete 3, and then you need to union the 3 table. So this is very close with the concept of fragmentation property. So if we do a fragmentation, let's say from the 1 table, we do fragment to 3 fragments, and then after that we need, when we want to reconstruct 3 fragments, we in the end we also have the original one. So this is reconstructability. So this one is union, and then the next one is difference. Difference is the difference between relation R and relation S. And the last one is Cartesian product, which is we combine all the possible combination from R and from S, right? And the next thing is relational algebra operation complexity. So don't worry too much about this one because this is not the main focus in this course. I think you study about this complexity one when you take a course like algorithm and data structure. So you got and that subject maybe you will study about the big O complexity and etc. The important thing here is like if we do a selection project without duplicate elimination, we got ON. And if we do a project without duplicate elimination by group by, we got O and log n. And join, semi-join, division, set operator, O and log n. For the Cartesian product is O n quadrat. And this is the tree of the O log n, something like that. Don't worry too much about this one. So if you go to your practical session, and in the task number 4, if I'm not mistaken, the practical one, you need to enable the statistic on your Oracle. So when you execute a query, the statistic will come, like how long this query takes, and then how many bytes that send from the sent to the client, and etc. So this is really related to that one, the complexity. Okay, now we go to the first step, which is the first layer of the query processing, which is query decomposition. So what is query decomposition? So let's consider we have this input query. We have this query here. Select employee name from employee table and from assignment table, and then we do join, where the employee number from the employee table equal to employee number from the assignment table, and the project number from the assignment table equal to P1, and the duration equal to 12, or duration equal to 24, right? And if we write this query in the form of tree, you can see in this side, right? So we have two table here, and then we want to join it. We have table employee, and then we have table assignment, and then we do a join with the based on the employee number, and then after that we do condition, or we do selection here using we have three condition here: project number equal to P1, duration and duration equal to 12, or duration equal to 24. And then finally we select, or we project it. Okay. And in this step, in this layer, in the query decomposition, nothing to do with the distribution of data. So this is exactly same for centralized and for distributed system. Nothing to do with the distributed data in this layer. Okay. And the next is still query decomposition. So the objective is same as the centralized DBMS, because in the centralized one or in the distributed one, we still have the similar condition, but we have to pay attention with this 3-1. So semantically correct, redundant work is avoided, better query performance. And to pay attention with these 3-1s, usually for the query decomposition layer, we will do normalization, analysis, redundancy removal, or rewrite. And what is those kind of step? Okay, we will go one by one. Okay, first, normalization. I will not much explaining about this one because this is like the basic knowledge from the database. Like maybe you got it from INFS3200 or another subject. But the point here is like we need to do we need to normalize if our table is not normalized. And we have the conjunctive normal form, which is using n here. So this one, and this is conjunctive, and the second one is disjunctive normal form, which is using O. Okay. And then the next step is analysis. So in this step, you have to pay attention with the type and correct, for example. So what is the type incorrect? Let's say in your query, you have something like this: birthday greater than 20. So this doesn't make any sense, right? Or maybe another example is like your name less than 5. So this one doesn't make any sense, right? So you need to remove this type incorrect. And then the next one is semantically incorrect. You can see this example of query, and then let's see what is missing in this query. Okay. First, select ename, employee name, and responsibility from employee table, still correct, assignment, okay, and then project, okay. So in this one, we want to select two data, two column, two attributes from this three table. And then after that, from this one, I expect that I will have a join here, right? And then this is the join clause where the employee number from the employee table equal to the employee number from the assignment. And then suddenly, and pname equal to CID or CAM. And this pname, if you see in this you see this one, wait a second. Yeah, I'm not sure. Maybe I need to move. Yeah, it should be back, right? Hi, Linton. How about now? Okay, yeah. Yeah, I'm not sure what happened with my internet connection. Okay, now it's clear, right? Yeah, thank you. So if you see this one, you will see that this is no connection. So project name, this one, from the project, there is no join anymore to this one. So there is no connection here. So that's why this query, that's why something missing in this query, right? So this is, we call it semantically incorrect. So you need to fix this query. So that is the point in this one. Okay. And then the next one is elimination of redundancy. Okay. Okay. Let's say we have this query. Right? And this is really nice example. Okay, select title. Okay, see, we want to select a title from employee table where title is not programmer, and then title is programmer. So this is really redundant and really doesn't make any sense. So this is useless. So that's why we don't need these two statements. This is really useless, right? And then we can go to the next line, or title is equal to electrical engineering, and not title is not equal to electrical engineering, which is these two also useless because this statement is negation of this statement. So we don't need this one, right? So this is redundancy. And then in the end, or employee name equal to John Doe, right? So this is only the correct statement. So 1, 2, 3. And the other statement are incorrect, right? Because they are useless. And if you put it here, like let's say the predicate 1 is title equal to programmer, predicate 2 title is equal to electrical engineering, predicate 3 name equal to John Doe, and then you put in this symbol, and then you will see that in the end you only have a P3. Okay, and this is the final query. This one, select title from employee where name equal to John Doe. So that's why you need to pay attention when you write a query. You need to eliminate any redundancy, and then you also need to eliminate any semantically incorrect or type incorrect. And you need to the correct one. So this query is exactly same with this one, but we have something missing here. Okay, let's say we have this query. Wait a second, why it's not. Okay, we have this query. Select employee name from project, assignment, and employee, where the number of employee in assignment table equal to number of the employee number from the employee table, and the project number from the assignment equal to project number from the project table, and the employee name is not equal to John Doe, and the project P name is equal to CID or CIM, where and duration equal to 12 or duration equal to 24. If you translate this one in the form of this tree, you can see this one. So in this query, we want to join between two tables, assignment and employee. This one, assignment and employee, right? And then after we do join here, because we need the project name, so we will join with the project table here, right? We will join here based on the project name. And then after that, we put the condition. We put condition, ename not equal to John Doe. We put the condition again, pname project name is equal to CM. We put the condition again, duration equal to 12 or duration equal to 24. And then in the end, we do projection, select employee name, right? So this is join, this is selection, and this is project. You can imagine if you have million rows of the project, million rows of the assignment, million rows of the employee. Here, first you need to do join all the rows in employee table and assignment table. And then we get the join. After that, we need to join the result from these two join table to the project table. If these three tables have million of rows, this is the problem. We will get the complexity problem. So what's a possible solution to make this query more efficient? This is one of the possible answer. One of the possible answer is push down where condition. So here in this one, we put where after we join the table, right? So we can push down this one before doing a join. And this is the example. Here. You see, this is one of the possible solution. So this is the table project. This is the assignment, table assignment. This is the employee, right? If we pay attention in the query here, we want to select employee name that not equal to John Doe. We want to select the project name that equal to CID or CIM, and duration is 12 or duration equal to 24, right? And if we pay attention, this P name, this project name equal to CID or CIM is only available in the project table. And this duration is only available in the assignment table. You can see the question here, right? So this duration is only available in the assignment table. Project name is only available in the project table. And then the employee name is only available in the employee table, right? So why we don't just put the where clause before we do a join here? So we do a filter here, just only select the rows in the project that P name is equal to this one. And we only select the assignment rows that satisfy this condition. We only select the employees rows that satisfy this condition. After that, we do join. After that, we select, this is the select that satisfy this condition, and then we do join here. We do join, and then selection again, right? And then here, the selection result from here, we do join here. And finally, this is the projection. Select ename, right? So that is the point. So you can observe to see more detail and then compare this query and this one, right? So in this one, you do a join first and then doing a where condition or selection. In this one, we do selection first and then do join. So in this one, it's more efficient because we do a filter first. We just select or we just filter the rows. So we just select the project name that equal to CID or CAM. Because what's the point that we bring all the rows in the project, all the rows in the assignment, and all the rows in the employee, and then do a join? What's the point? Because we already know that we're looking for this one, we're looking for this one, we're looking for this one. So that is the point why we need to rewrite a query in query decomposition layer. Okay, so that is the query decomposition layer. The next step is, the next layer is data localization. Okay, so what is the data localization? In query decomposition layer, we do not consider about fragmentation. We do not consider about distributed design because it's exactly same between centralized and distributed one for the query decomposition. But for the data localization, we consider the fragment. So we need to consider the distribution of data, the fragment. Here, the input is relational algebra query from data decomposition, and the output is algebraic query expressed on physical fragment. So from this query, let's say from this query, how we translate to our fragment, right? And the objective is consider the data distribution, localize the query's data using data distribution information in the fragment schema. Okay, and this is the data localization. Maybe I just want to explain quick. So the point in this one is like this. Let's say you have 3 fragments on your employee table. This is the employee. This is the first fragment of the table employee. Let's say the fragment employee 1, and this is the fragment employee 2, and this is the fragment employee 3, right? And then you have a query. You have a query. You want to execute a query here. You want to execute query here, right? You want to execute a query, but you don't know this fragment. So you know that the table employee is fragmented. Table employee is fragmented to 3 fragments, but you don't know the predicate on the fragment, right? And then you don't know the data that you are looking for. So in that case, you need to union all the fragment to the single again. So this is the concept of the reconstructability. So if you want to execute query, you need to union all the 3 fragments and become the employee table and then execute the query queue, right? But the point is, let's say we know the predicate. The fragment of the employee 1 table is when the employee number, employee number is, let's say, less than 4. And then this second fragment predicate is employee number less than 7 and greater or equal than 5. Let's say, right? And for the 3 fragment, larger or equal to 7, let's say. And then we want to get the data that the employee number is equal to A5. Employee number is equal to A5, which is, if we know the predicate of the fragmentation, we really sure that this A5 is only available in the fragment 2, in the employee 2, right? Because the employee 2 fragment, the predicate of the employee 2 fragmentation is the employee number less than 7 and greater or equal to 5. And 5 is included in this one. So that's why instead of using this 3 fragment, if we know the fragmentation predicate and we know what data that we're looking for, so we don't need to consider this to fragment, so only consider the fragment 2, something like this. So this is the reduced query. Okay, so this is the localized query, and this is reduced query. So that is the point in this slide. Okay, any question? So if no question, I can go to the next step, which is the global optimization. Okay, global optimization. So the input of the global optimization is reduce query on fragment. This one, this is the input of the global optimization, and then the output is query execution plan that minimize the objective cost function and communication operation. So this is the question, still question 1 in global optimization. So you have to pay attention with this one. This is really important in this slide, in this presentation. Okay, wait a second. So when you write a query and then you want to execute a query, you have to pay attention with these 3 things. The first is search space, second is cost model function, and then third is search strategy or algorithm. And the things that you need to more pay attention is this one. Okay, sorry, it's really hard to to draw. Okay, when you execute a query on your standalone laptop, your query will need these 2 costs, right? Which is the I/O cost is the hard drive cost. So let's say when you do a practical, you import or execute SQL script on your SQL developer. So is that mean your Oracle will write the data on your disk. So that's why it's need I/O cost. And the CPU is to executing the task, right? But because in this course we focus on distributed database design, so we have a communication cost, and these communication costs mostly are greater than the I/O cost and CPU cost. You can imagine that. Let's say you have a laptop, right? You have a laptop, and then you want to execute a query on your laptop, but that query needs to join another table, and that another table is out of your laptop, which is in another network. So you need to download or you need to copy the table that you need for join from another network or from another system to your computer. So that's why communication cost is costly in the distributed database design, right? And this is the one of the example of the solution space or the execution plan, for example. So let's say for this B, we get 10 cores. And then for this E, we got 12 cores. So which one that we choose? This one, because the cheapest one. So 10 is cheaper than 12. Even, let's say, even the 10, this one has more step than this one. Even this one has more step than this one, but we need to choose the cheapest cost one, right? So that's the point in this slide. And okay, so we go to the question 2. So the question 1, query decomposition, and then query decomposition, query decomposition, data localization, and global optimization. Query decomposition is how we decompose the query, and then data localization when we consider the fragment. So from the localized query, we make a reduced query if we know the exactly data what we want to looking for, and then we know the predicate of the fragmentation. And then the last one is global optimization. All right, and in the global optimization, we need to consider the cost. Okay, so the question 2, localization. This is really interesting practice. So let's say we have 4 tables here: employee, assignment, project, and payment table. And then let's consider we have two predicate for the fragmentation. So the first fragment is project number less than or equal to P2. So this is the first fragment, right? And the second fragment is project number greater than P2, which is P3 and P4. Okay, this is the first fragment, this is the second fragment, right? And then with this following query, select employee number, project name. So we do join project table and assignment, where the project number of the project table equal to project number in the assignment table, and project number equal to P4, right? So with this following query, we can imagine, right? So we have the condition here. So if we step back to the previous slide that I explained to you, we can optimize this query by not do a join in the first step, but push down the where condition and etc. But let's see what happened in the next slide. So with this following query, we need to reduce the query on fragment, okay? Because in this case, the project table has two fragments, and this is the solution. Okay, so this is the original one without any fragmentation, right? This is the original one. So we have the project table, we have the assignment table. We do a join based on the project number. And then after that, we put the condition here where project number equal to P4, and then we do a projection, select in employee number and project name, right? And because we already have two fragments for the project 1 and project 2 here, and if we don't know this one, or if we don't know the predicate in the fragment 1 and fragment 2, we need to bring back this project 1 and project 2 fragment to the union project, which is we need to bring back to the project and then execute a query. But because we already know the condition here, so in this one, we know that we looking for project number equal to P4. And this P4 is, if we see the fragmentation here, this one, so P4 is only available in the fragment 2, right? In the project 2 fragment here, okay? So that's why in this one, we don't need to consider the project 1 fragment here. So we don't need to consider the project 1 fragment. So instead of using select from the project, the whole project, or using the project 1 and project 2, which means the whole project, so we do not include this project 1. So only project 2 that included, right? So you got my point, right? Because we know that we are looking for P4, which P4 is in the project 2 fragment. So that's why we don't need to include project 1. And if we write in the tree, you can see something like this. So instead of using project, or project is the union between project 1 and project 2, so we use the project 2 only. So we do join the project 2 and assignment based on the project number, and then we put the condition here where the project number equal to P4, and then we do a projection, select employee number and project name. So this is the form of reduced query. And then how about the optimized one? Can we optimize this one? Yeah, because we know this condition, right? We can push down this one before the join. So we do filtering first, then join. So in this case, we will select all the project in all the data, all the rows in the fragment project 2, all the rows in the assignment table. But if we push down the condition here, so we do a filtering first. We only select rows in the project 2 fragment that satisfy this condition. We only select rows in the assignment table that satisfy this condition. So after that, we do a join, which is the join cost will really cheaper compared to this one, right? And then in the end, we do projection. Select employee number and project name. Okay, does it make any sense? Clear, right? Okay. No question. So the second question, number 2. So question 2B. Yeah, 2B. So we still have a fragment for the project, and then we have more fragment here. We have more fragment for the assignment table. So here, if we see this condition, the predicate here, see. So the predicate one is employee, sorry, in the table assignment, the project number is less or equal to P2. So this one, this is the first fragment, right? And then the second fragment is project number is less or equal to P3 and greater than P2. So, okay, so because this is not sorted, so yeah, so the first fragment will be this one and this one and this one, yeah. And then the second fragment will be only P3, right? Only P3, this is the second fragment. And then the third fragment is greater than P3, which is only P4, right? So we have 3 fragments on the assignment project, assignment table. Okay, and with this following query, we need to process to reduce query on fragment and then determine whether it is better than the localized query. Okay, so this is the localized query. You see here, we have 2 fragments for the project, which is fragment project 1 and fragment project 2. And then we have 3 fragments on the assignment. So assignment 1, assignment 2, and assignment 3. We need to bring up by union it together, bring back the project and assignment. So this is in the case of distributed database, right? So if we have query, we need to bring up the project, union it again. We need to union the assignment and then do a join, and then do a where clause, and then in the end we do a projection, right? So this is the localized one. And the next step is how about the reduce with the join. So to reduce this query, we have 2 fragments on the project table, and then we have 3 fragments on the assignment table, right? So we need to compute, or we need to write the all possible combination of the join. So this one, the all possible combination will be 1, 2, 3, 4, 5, 6 possible combination. Project 1 with assignment 1, project 1 with assignment 2, project 1 with assignment 3, which the total number will be n 2 po with the n, right? So you still remember the tutorial 1. And when we after we write down the all possible combination of the join, we need to verify is that join valid or not valid. So let's say this one. So in this one, the fragmentation of the project, where the project number is less than or equal to P2, we do join with the project number less than or equal to P2 from the assignment table, which is, this is makes sense, right? There is a data here. This join is valid. But let's see the black one. This one is project number greater than P2, and then from the assignment, project number less or equal to P2, which is doesn't make any sense because this is greater than P2 and this is less or equal to P2. There is no overlap, right? So that's why this is invalid. So here, there is only 3 join that valid, right? Okay, and then let's see here, and this is the reduced one. So instead of we have 6 possible combination of join, so now we only have 3 possible of the valid join: project 1 and assignment 1, project 2 and assignment 2, project 2 and assignment 3, right? And then we do a join, we do a join, we do a join. After that, we bring up union, we bring up by unionate, and then put the where condition, and then go with the projection, right? And then, so the question is that better, reduced query compared to the localized one? It's same, right? But in the parallel computation, wait a second. So this is the comparison of this one, right? And the point in this one is, can we also optimize this query, like put down or move down the where condition here before the join? Nope, we couldn't do that. Because the problem here is the data that we're looking for is the project name, which is we don't have a project name here, right? We only have the project number. Let's say if the project number is equal to P3, so the data that we're looking for is project equal to P3, and then we can bring down before the join. So that is the difference between this task with the previous one. Okay, so if no question, we go to the question 3, which is the quite complex one, but really interesting. And this question 3 is really related to your practical task number 4, practical 1, number 4. So at that task, you need to do a join, and then you need to compute the complexity. Okay, let's see here. So this is really interesting example. Let's say we have 2 table. Let's say we have 2 table or 2 relation. The relation R consists of this table, and the relation S consists of this table, right? And we have different side. So R in the side 1 and S in the side 2, right? In this case, the cost that only we consider is the communication cost or network cost, because in the context of distributed database design, the network cost or communication cost is really costly, right? So if we want to send R to site 2, send R to site 2 here, if we want to send R to site 2 here, the cost is 10, because R has 10 cells, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So R has 10 cells, so the cost is 10. So if we want to send R to to site 2, the cost is 10. The opposite one, if we want to send S to site 1, the cost is 12, because we have 12 cells on S, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So if we want to do a full join, these 2 tables, if we do join here, if we do join here in the side 1, if we want to execute query here, so we need to copy file, we need to download the S to this side 1, which is the cost is 12, right? But if we want to execute the query in this one, in the side 2, if we want to execute the query in the side 2 here, if we want to execute query in the side 2, we need to copy R from the side 1 to side 2, which is the cost is 10. And 10 is less than 12. So that's why in this condition, I prefer to execute query in side 2 because it's cheaper, right? And is there any another way to get more cheaper costs? Let's see here. We call it semi-join. So what is the semi-join? Here. So in a semi-join, in this case, if we want to perform a full join, like what I explained before. So if we want to execute in the side 2, we need to copy whole the data, whole R to S, and then do join on the side 2. With the semi-join, instead of copy all the things, we just only copy the distinct values. So if we see the relation, R and S, right? So we have the common column, which is B, right? And this one, if we do join, it will be based on the B because these two table has the common attribute. And to do semi-join, we do select distinct. Select distinct. Okay, we do a select distinct. So select distinct means just get the unique one. Let's say if we want to select distinct P, the result will be 4 and 5 because P only consists of 4 and 5, right? The purpose of select distinct is, so in this condition, because we don't know exactly, okay, if we want to execute in the side 2, we don't know R. We don't know the table in the side 1, right? So that's why we don't know all the table. If we want to execute in the side 1, we don't know S, right? So that's why we need to download it. So by select this thing, and then we just only send this SP to the side 1, let's say, and then do semi-join in the side, and then bring back to the side 2 again. This might get cheaper cost, but it also generate a higher cost. Let's see this one. So the question 3 number 1 is how if we do a semi-join R and S. So this is R. So S here, we just do a select distinct, right? We do a select distinct. We got 4 and 5. And 4 and 5, the cost of sending 4 and 5 from side 2 to side 1 is 2 because it only has 2, right? And then after we sending this 4 and 5, we do semi-join, not full join. This is only semi-join. We do semi-join this SP that already sent to side 1. We do semi-join with the A. And this is the result of the semi-join, right? And for the next question is how if we do semi-join S and R. So let's say we select distinct R, we got this one. So RB is 4, 5, 6, and 7. 4, 5, 6, and 7. So only number 4 that has a duplicate. So if we want to send this distinct result from the set 1 to set 2, we need cost 1, 2, 3, 4. 4 costs, right? And then after that, we do a semi-join here. We do semi-join, and this is the result. This is a semi-join, not the full join, right? So the question is the semi-join. Okay, and then the last question. This is the really nice one. Okay, the last slide and last question. So let's assume that you want to issue or you want to execute the query in set 1 and set 2. you want to perform the full join here in side 2. And we want to use semi-join here, right? So this one is the separator. This one is the, so this one is side 1, this one is side 2, right? The first thing that we need to do, because we want to execute in the side 2, we select these things as B, right? So we got 4 and 2. And then we will send 4 and 2 to side 1. The cost is 2. The cost is 2, right? And then after we send it, we perform semi-join here. We perform semi-join. And then we need to send this result, semi-join, send back to the side 2, right? Because we want to perform the full join on the side 2. So we need to send this one. The cost is 6, right? 1, 2, 3, 4, 5, 6. The cost is 6. So 6 plus 2 is equal to 8. And this is less than 10. So if we do like directly full join here in the side 2, this one, if we do directly full join in the side 2, which is by copy R, all R to side 2, the cost is 10. And using semi-join, we can reduce 2 costs because the total cost is 8, right? Does it make sense? But you need to try at home. How if we do the opposite one? How if we want to execute in the side 1? This is really interesting. So for example, like this one. So if we want to execute in the side 1. So let's say we have this one, right? We have this one. So this is side 1, and this is side 2, right? So we want to execute in this side 1 using semi-join. So first we select this thing. We got this one, right? We got this result, and the cost is 1, 2, 3, 4, 4. And then we send it to side 2. And then after that, we perform a semi-join here. We perform a semi-join here. We perform a semi-join. And this semi-join result, we need to send back to side 1, right? Because we want to execute the full join in the side 1. So the cost is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The cost is 12, right? So 12 plus 4. So this will generate higher cost compared to if we just directly execute in the side 1, which is by the copy of the whole data, the S. We just copy the S to the side 1, it only costs 12. But if we do with the semi-join, the cost is 12 plus 4. Okay, so that is the point in this slide. I think that is enough. So let me know if you have any question. We still have 3 minutes. If no question, so this slide will be available after Friday afternoon. But if you want to get it right now, I can share it to you here. Wait a second. Can anyone confirm that you can open the slide and see the slide? Do you see the slide? I just put it on the chat. Okay. Okay, thank you so much for watching, and see you next week. I will end this session. Bye-bye, everyone.